Hi everybody. So in this lesson we're going to look at kinematics, which is the study of the motion of objects. So we're going to look at how objects move, which includes displacement, velocity, acceleration, distance traveled, and speed. So firstly, let me bring your attention to some of these terms. Displacement, velocity, acceleration. What are they? Okay, well, displacement, displacement is, there's a strong connection between displacement and distance, but be careful, there is a big difference between the two. Imagine you lived here, and your friend lives, let's say your friend lives 2 kilometers to the south. So you live here, your friend lives here, and this is 2 kilometers. Now, if you walk to your friend's house straight down here, you will travel a distance of 2 kilometers, and your displacement will be 2 kilometers south. So displacement has direction in it as well, whereas distance does not. But imagine you wanted to go to your friend's house, but you wanted to go via, I don't know, let's say via the shop, or via something that's on over here, and you might even want to go and see someone else that's there, and then you come back. It might even be that this is the road to get there. There isn't a direct straight road from your house to his house. Now if this is, let's say this is 4 and this is 1 and this is 5. Now if you go this way to your friend's house, you will travel a distance of 10 kilometers, but your displacement will still be 2 kilometers south. And actually if you walk all the way home, if you do this, go to his house and then walk home, your displacement is 0, because you are 0 kilometers or meters or whatever from where you left, from your starting point. So that's the difference between displacement and distance traveled. Fine. Velocity and speed, they are also very closely linked, but one of them has direction and one of them doesn't. So let's say you are, and I'm going to actually use this analogy for my example here. Imagine we're driving in a car and we're going, let's say 100 kilometers an hour this way. Your velocity is 100 kilometers per hour, and your speed is 100 kilometers per hour. But if you then start reversing, or just going backwards, or just going the other direction, let's say you start going this way. I like to think of it as reversing, but certainly you could just turn the car around, but you're driving the other direction. This is then negative. So your velocity is now negative. Let's say you are reversing, so you're going a lot slower. Let's say negative 20 kilometers per hour. Your velocity is now negative 20, but your speed is still 20. When you're reversing in a car, you don't say to someone, oh, my speed, I'm going negative 20 kilometers per hour. You just say I'm going 20 kilometers per hour in reverse. Okay, so that's the difference between speed and velocity. Acceleration is just the rate of change of velocity. So again, I like the car example, because if you press the accelerator, you start to accelerate. Your velocity starts increasing and you start going faster and faster and faster. That means you're accelerating. If you press the brake, you will start to decelerate. Now I'm going to, I'm not going to use the word decelerate unless I'm explaining something like this. Instead of using decelerate, I'm just going to say my acceleration is negative. And this leads me nicely to these rules in the formula booklet. So displacement, we use the letter S to tell us the displacement. Velocity is V, acceleration is A. Those two are easy. Why do we use S and not D? Well, D is, you could get confused with distance, so we're going to go with S. Right, so the displacement is S. Now the rate of change of displacement with respect to time is what velocity is. Look, if you are going 100 kilometers per hour, that means your displacement is changing by 100 kilometers every hour. So this is a really nice, it's actually a really nice and useful application of calculus that we can actually differentiate. If we differentiate this displacement, this ds dt, we get ds dt, just differentiate displacement with respect to time. So it's the change in this change in displacement with respect to time. That, sorry, I didn't want to put that there. That gives us the velocity. The velocity is the change in displacement with respect to time. And then what's acceleration? Well, acceleration is the change in velocity with respect to time. It's how my velocity is changing. I'm getting faster and faster if I press the accelerator. So it's dv dt. And it's there in the formula booklet. Now they don't give us ds dt, but I guess they assume we should know that. But if we're saying v is ds dt, then dv dt is just the second derivative of this, which is d2s dt squared. So the second derivative will give me the acceleration. Okay, now that leads me to a little rhyme that I have to help us remember this. So if we have displacement, velocity, acceleration. To go this way, we differentiate. I'll just write diff. And then to go this way, I don't know why I'm using green and red, but I guess positive, negative. To go this way, we integrate. Because if I'm displacement to get to velocity, differentiate. If I'm in velocity to get to acceleration, differentiate. But we know to integrate is the reverse of differentiation. So if I want to go from acceleration to velocity, I integrate. And if I want to go from velocity to displacement, I integrate. So here I have SVA. The best rhyme that I've got, and I've asked many students to give me a rhyme, is so, it's not even a rhyme, but it's so very awesome. Something to remember this SVA, so very awesome. So SVA, differentiate to go to the right and integrate to go to the left. Okay, fine. Let us go into this example. So this is basically a past paper question that I've adapted slightly. I've actually made it a bit longer just to include all the different types of questions that you could be asked. No doubt the IB are able to come up with very difficult, strange questions that you haven't seen before, but hopefully if you understand how to do all of this, you will be able to at least give them give every question that you might get a good attempt. Obviously, practice the past paper questions once you've finished watching this video. Okay, so a particle P. There's a particle P, it's moving along a straight line so that its velocity v meters per second after t seconds is given by this. So this is a velocity function, and this is a velocity time graph. The x-axis is time, the y-axis is velocity. It's not x and y, it's t and v. So time and velocity, and this tells us what its velocity is after a certain amount of time. Find the initial velocity of p. Okay, let's begin. So before we actually do that question, I want to look at the graph and I want you to think about what's actually happening to this particle, and let's actually think of it as a car. So we have a car moving in, the car is moving in a straight line. So let's think of it as it's going forwards, and then it goes straight into reverse and it goes backwards. So what's actually happening at this point here? Now the graph, the gradient of the graph is negative, or it's decreasing, but that doesn't mean the car is going backwards. At this point, at the very beginning, the car is going forwards because its velocity is positive. So its velocity is positive here, and it's positive all the way down to that point there, which is that is a 0. It's where his velocity is 0. So he's going forwards, and he's slowing down, and right at this point his velocity is 0, so he stops instantaneously, immediately goes into reverse, and now he starts going backwards. So he's actually going backwards all the way along here because velocity is negative. Even though there's some turning points in the road, or there's some turning points in the time, he is going backwards all the way to here. At this point then, he instantaneously goes into first gear. He stops like instantaneously, goes into first gear and goes forwards. So he's going forwards, backwards, forwards. Now what is happening at these kind of turning points? Well, he is he's reversing here, but he's getting faster and faster and faster and faster. So he's going backwards, but he's put his foot on the accelerator. So his acceleration is negative here, but he is going faster and faster, and he is decelerating, if you want to think of it as that word. So he's decelerating to here, and then he decides, hang on, I'm going too fast, I'm going to slow down a bit, but I'm still in reverse, but I'm going to slow down a bit. And then you go, oh, I'll speed up a little bit, and then I'm going to slow down a little bit, but it's all the time in reverse. And then straight away he goes into first gear, and now he starts to speed up, and he's going forwards, forwards, forwards. And then at this point he presses the brake and says, hang on, I'm going too fast, I'll slow down, and that's the end of it. So it only goes from 0 to 5 seconds. Now yes, if it's a car, this is all happening pretty quickly for 0 to 5 seconds. It isn't a car, it's a particle, but I like to use the car analogy because it helps to understand what's going on. Okay, so hopefully you have an idea of what's going on with that graph. Let's do these questions. The initial velocity of p. So initial velocity is when t is 0 at the start. So I'm trying to find v of 0. Now this is a calculator. I should have put the thing, my little drawing. This is a calculator allowed question. So we are allowed to use our calculator. But I'm going to show you how to do this without a calculator because it's straightforward. So v of 0 is 2 cos of 3 times 0, which is 0, minus 5 sine of 0, minus 1. This is actually, cos of 0 is 1, so it's 2 minus 0 minus 1, 2 minus 1 equals 1 meters per second. So his initial velocity is 1 meters per second. Fine, that's how to do it without a calculator. We have a calculator, so I'm going to show you how to do it with the calculator as well. Okay, let's do part B. The displacement of P after 5 seconds. So let me just get out this calculator. Right, I'm actually going to graph. I'm going to graph this function here. So let's do, it's 2 cos of 3t, so 2 cos of 3t, but I'm going to have to use x because this is my xy graph. So it's 2 cos of 3x, close my bracket. Where's my bracket gone? Here. Minus 5 sine of x, minus 5 sine of x, minus 1. Okay, does that look like this? Well, not exactly, because the domain is a lot bigger. I'm actually going to get the zoom to work a bit better. Now, because they've given me the graph, I like the Windows settings because I can just put the settings to what they have, like 0 to 5 and let's say negative 10 to 5. But I'd actually prefer to go a little bit more than what they give me. So I'm going to go from negative 1 to 6, and I'll go from negative 10 to, let's go to 8. See how that looks. Okay, fine. Now, the initial, let's do that part A with the calculator. If I go to trace, so I like this trace button. If I go to menu trace, and I can move along here, it finds me my minimums, my 0, and at this point the y-intercept, look, the y-intercept is 0, 1. 0 is the time, the x-coordinate's the time, when t is 0, and the y-coordinate is the velocity. So the velocity is 1, and there you have it. In a calculator question, you wouldn't even have to, I would write v of 0, but look, if you just put down 1 meters per second, you'd actually get all the marks. Second one, the displacement of p after 5 seconds, right? Now if we go to this formula, the displacement is the integral of the velocity. So remember I said to get from velocity to displacement, we integrate. So it's the integral from t1 to t2. t1 will be 0 and t2 will be 5. So the integral from 0 to 5 of the function, which is 2 cos 3t minus 5 sine t minus 1 dt. And here, look, if this is a paper 2, you do not have to integrate it. I don't have to go to the process of getting sine of 3t over 3 and whatever it is. I can just type that into the calculator. So here I'm going to go menu, calculus, numerical integral. I'm going to go from 0 to 5, and then I'm going to go 2 cos. I can actually use t here, so I'm going to go 3t, 2 cos of 3t minus 5 sine of t, and then minus 1, just make sure I now do dt here, press enter, and I get negative 8.14816. Negative 8.14816. Is that what I said? 8.14816, yes. So the displacement of p after 5 seconds is negative 8.14816 meters. So the negative is important, and look, the meters is important because that's where it is. And does it make sense that he'd actually be in a negative position? Well, if I look at this graph, I'd say yes, because he's reversing for a lot longer than he's going forwards. So it makes sense to me that he goes a little bit forwards, then a lot back, and then a little bit forwards again. So yeah, if I actually draw that, what's happening is he's going a little bit forwards. That's this bit. Then he goes a lot backwards, which would be like this. And then he goes a bit more forwards, a bit more than this, but not as much forwards as, certainly not enough to get back to the start. And that's why, look, this display, if this was his starting place, he starts here, goes a little bit forwards, a lot back, and then a bit more forwards. And this is his end point. This distance from here to here is his displacement, and it's negative because he's to the left of where he started. So that's his displacement. If I wanted to get the distance traveled, and look, that's this next question. The distance traveled is going to be this plus this plus this. But let me show you a nice, neat way to do it. Again, in the formula booklet, the distance traveled is the same formula, but this time with the modulus sign. And the reason for the modulus sign is because that gets rid of the negatives, and it will make this negative bit that we've traveled here, it'll make that positive. So it'll just add this plus this plus this. So the distance, the distance traveled is the integral from 0 to 5 of the modulus of 2 cos 3t minus 5 sine t minus 1 dt. So what working do you have to write down? Well, that's it. You have to write down the integral. You have to write down the integral, and then you can just write down the answer. What is this? So it's going to be positive, and it's definitely going to be more than 8.14. Let's find out what it is. So menu, calculus, numerical integral. I need 0 to 5, and here I want to put these modulus signs which are there, that, and I want to copy, Control C and Control V. I want to copy that in there. Perfect. And that's dt. Press enter. That's what I was expecting. 19.5613. So this is equal to 19.5613 0.5613. Okay, next one, CD. And that's and that's meters, and that's the total distance that he's traveled. D, how many times P changes direction? So remember, this is our car and we're going into reverse. Now look, the common incorrect answer here, as you can imagine, would be 1, 2, 3, 4. He changes direction 4 times. No, that is incorrect, because this is just when he starts to slow down, but he's reversing. He's still reversing. He's not changing directions. This is where he changes direction, and this is where he changes direction. So he changes direction twice. He goes from forwards to backwards, and then backwards to forwards. So the answer to this is just 2, and I can just write down 2 if you want to indicate here, or you could even write crosses T axis twice if you really want to show some working, but you definitely get full marks for that. Okay, E, find the acceleration of P after 3 seconds. How do I find acceleration? Well, here we are. Acceleration is the derivative of the velocity. Or here, look, I have the velocity. To get to acceleration, I differentiate. So I need to differentiate this thing, and it's after 3 seconds. So I want dv dt at 3 seconds when t equals 3. Now look, again, many students will start differentiating this and subbing in t. If it was a non-calculator paper, fine, yes, you have to do that. But this is with a calculator, so all I need to do is get out my calculator, do menu, calculus, numerical derivative at a point. I want x, I want 3, I want the first derivative, and I'm actually going to just paste this in again, Control V. So I want the derivative of this, at x equals 3, press enter. Oops, I did something wrong. Okay, because I did it, I used t here, and the derivative is with x. Right, let me do that again. I need menu, calculus, numerical derivative at a point, x. Okay, well actually I could just use t here. I could use t there. The value is 3. Now do my paste, Control V, press enter, and I get 2.47725. 2.47725. 2.47725. Now what that's telling me is, it's telling me the acceleration when t is 3. Now here's when t is 3. What is the acceleration here? Where the acceleration is the rate of change of the velocity, which is actually the gradient. It's the gradient of the curve at that point. And does that look like it might be, or that it could be a gradient of 2.47725? Well, yeah, it's positive. These axes aren't actually to the same scale, so that's absolutely fine. Yes, you can see he's starting to accelerate. So the acceleration of p after 3 seconds, yes, that is the acceleration of p after 3 seconds. He is accelerating, even though he's slowing down. And this is the thing I talked to you at the start. The car is slowing down because he's in reverse and he's slowing down, but technically he is accelerating. Okay, final question. Find the maximum speed of P. So I've thrown in this question to make sure you guys understand the difference between velocity and speed. So let's just find it on the graph. Where is the maximum velocity? This is velocity and this is time. Where's the maximum velocity? Well, it's certainly here. It's at that point somewhere over here. That would be the maximum velocity. But remember, this maximum speed, like speed, it doesn't matter if we're going forwards or backwards. Now this this guy's at this point, his speed is like 5 point something, maybe 6, but no, probably 5 point something. Whereas the speed at this point is like it's gonna be more than 5. So I need to find, well, we'll check both on the graph, but I'm pretty confident from looking at the graph that his maximum speed is going to be here. Okay, let's get the graph. So it's either going to be this one or this one. And we do our menu, analyze graph. I'm going to get my minimum, lower bound, upper bound. So here it's negative 7.471, and this guy, I'll do the maximum, is 5.471. Now note, I am looking at the y coordinate because that's the velocity. This is the time, that's the velocity. Time, velocity. His velocity is obviously more than his velocity, but his speed is bigger than his speed. So the maximum speed of the car is 7.471. 7.471. Max speed is 7.471 meters per second. And look, that little bit of drawing that I've done on the graph is certainly enough working. You could also say happens, if you really wanted to say happens when t equals 1.16. 1.16. Okay, that's it. So obviously I've gone through a lot there. Kinematics is quite a big topic, and I've taught it all to you in one lesson. If you understand everything I've done there, fantastic, you're in very good shape. I would actually advise you to even try and do that question I've just done again yourself, and then watch the video after, just to make sure you know what you're doing and that you've got it correct. The key points to note are, obviously you know what displacement, velocity and acceleration are. This SVA thing, differentiate to get from displacement to velocity and velocity to acceleration, and then integrate to go backwards. And then when you are given a velocity time graph, to make sure you understand what's actually happening. Is the particle going forwards or backwards? Also, be careful. Sometimes they don't give you a velocity time graph. They can give you a displacement time graph, and it's even possible they can give you an acceleration time graph. So don't assume that it's velocity. Read the question and make sure you follow exactly what they say.